Thank you very much. It's a pleasure to be here. So today I'm going to talk about basically what I've been doing in the past few years, and also so there's going to be a bit of research, but also a lot of speculation and ideas that are not completely formalized or specified. So I think for me it's an opportunity to try these ideas and get feedback from you. So don't hesitate to interrupt. I may not be able to get to the end of my slides, but it's not really a problem. I intend this more as an interactive session than a lecture. So I've been working in the past, basically throughout my careers in developmental psychology, and I've always been interested in how artificial intelligence, machine learning could connect to this field of research, which is primarily empirical. I think for me, the motivation of making this connection is that I think one of the problems we have in psychology is that very often we do a lot of experiments, which is fine, but then we don't have a lot of ideas about how to interpret these experiments in a more theoretical framework. And so the hope for me in going this field was that maybe machine learning could provide a part of that framework. So developmental AI is actually a very old idea. Has been formulated not with this name, but the idea was formulated by Alan Turing by saying that if you want to build an artificial mind, the best way to do it is to simulate a child, because then if you have a child which supposedly has a simpler architecture than the adult, you just need to teach and interact with the child, and it will just spontaneously emerge into an adult. So already you can see that this way of looking at artificial intelligence is not what's being done in the standard way in machine learning, okay? Because in standard machine learning looks more like this, where you have a human expert looking at a large data set and providing labels. And the way in which you do machine learning is that you have truly something that learns, but it learns through association between this input data and the labels provided by the human at a very large scale. So if you make the analogy with the child learning language, it would be more like the way in which education was envisioned in the 19th century, or maybe it's called also the Prussian system, where you really force feed a lot of information. The child has to memorize everything by heart. That would be the way in which machine learning is done currently. So it's very far from what the child is doing. And this has a problem that has been identified, and I can illustrate here in a standard problem in machine learning, which is ASR. ASR means artificial speech recognition, automatic speech recognition. So if you talk to your phone, now your phone can recognize what you say, and you can ask questions about what time it is and where to go from one point to the next. You input some speech, and then you have a system that has been trained to recognize that speech and convert that into text. And that has been done with a lot of data annotated by human. On this scale here, you have the number of hours that it takes to train a state-of-the-art speech recognition system, ASR system. So the Microsoft a couple of years ago claimed to have reached the same level as a human in doing this task with 2,000 hours of speech. The Baidu system is trained with 12,000 hours, and then you have a sort of a prototype at Google which goes up the scale. You can't even represent that in the same scale. So typically, the system that you are using on your phone, deployed on Android or Siri, is somewhere in between these two. So it's a lot of hours that has been annotated by hand. And not only that, actually, when you build a speech recognition system, you also need a lot of text to do what's called language modeling. So language modeling is basically a way to compute the probability of a sentence. That's sort of a top-down component to speech recognition. The speech recognizer provides possibilities for interpreting the speech into phonemes or words, and then the language model tells you how probable the sentence is. When you combine these two, you compute the probability of the sentence given the speech. Okay, and that's a billion words of text. Yes?
Naive question. So, usually this is done in the lab, the learning.
Yeah.
And how do they implement that? Do they implement it over fork? Do you mean you come out with some software which does this?
Oh, so
what is the size
well,
of the software?
Currently, the software, I mean, this function is done by a deep neural network with many parameters.
Which is not done locally on your phone?
No, it's on the cloud. It's on the cloud. It's on the cloud, yeah. Yeah. Okay, so now all of this has a cost, the cost of collecting all this data. And here I represent on the x-axis languages. So each of these point here is a language in the world. You have around 7,000 languages in the world. And on the y-axis, you have the number of speakers that speak that language. And you can see that you have a power law, extremely sharp. And basically, Google plans to provide a speech recognition system for only 60 languages, which is less than 1% of the languages of the world. So what happened with the other 99% of the languages, given that half of them don't even have an orthographic system at all? So you can't even train your system because you need this parallel corpus of speech and text. If you don't have text, you can't do anything. Okay, so actually, even in a language with a lot of resources like English, it's a problem because you have lots of different dialects, and also people don't really speak in the same way as they write. So you have a mismatch between the text that you can collect to train your system and the way in which people are using the language in real life. So, of course, we know that infants don't need all these resources to talk to you, to learn to talk and speak. On this graph, we represented the number of hours that a 4-year-old toddler has heard directed to him or her during these 4 years of life across different populations. Well, there are several, I mean, this graph is interesting for several reasons. One is that there is actually a lot of difference between cultures. So this is in the US, in a high-income family. This is in the US, in a low-income family. There's already a fourfold difference in the amount of speech that the infants are hearing. And here you have a Tsimane population, which is a hunter-gatherer population with even less data. Yes?
What does the amount of speech mean in this case? Is this the
number of hours. Number of hours. So it's on the same scale as the system. So you can see that roughly the average child in high-income US families here a little bit less than has been. I mean, typically, as I said, the typical ASR system is way over the scale there. So there is already a big difference. But then if you consider that these kids can still learn to speak and they speak to you and they have perfectly okay language with much less data. Actually, there's another difference. Yeah.
I don't think it's the same unit on this graph because the other one is maybe better processor or something, because otherwise it would be.
Sorry?
It cannot be the real unit of the speak, because otherwise it would be, you know, a year is 4,000 years. Hours.
Yes.
So you cannot add in real hour this number. It's number of processor.
I don't understand the question.
So you say 125,000 hours. So clearly these are not real hours. Maybe they are real hours per processor or something like that.
No. These are real hours of speech that has been annotated. You are talking about these numbers? Yeah, so this is the number that's the size of the recording you need to train an ASR system.
If that was the case, then there would be not enough time.
It can be parallel, I suppose. You
That's needed to train. That's needed to train the system. But once it's trained, it can.
It's not the real time.
It's not the training time, it's not the training.
No, it's not training time. It's the number of hours of speech. It's the data set size.
The training sets.
It's the size of the training set. So it's a lot of. It's actually. It costs a lot of. I mean, when you build a speech recognizer, it's of the order of $10 million to build that, because you need to record all this vast amount of data and then have someone type everything. So it's a lot of data. And so the other difference between the child and the machine is that the child not only needs less number of hours, but also no text. At 4 years of age, the babies don't know yet to read and write. So
just to follow you a bit there, how's the human data taken there?
So the human data. So this is a paper that we wrote with Alex Christia in my lab. So this is a bit heterogeneous, right? So each of these studies have been using different ways to estimate that. These studies have been using recorders that you put in a baby pocket, and then you sample at random times. This one, the Timane one, is the most striking one, but that has been done with anthropological measures. So you have someone writing at random intervals what the child is talking, what's going on in the environment of the child. So this may be less precise, and we're actually trying to redo that with more precise measures. Yes?
But this measure is kind of unfair to the computer, right? Because a 4-year-old kid has a lot of sensory data coming in every time. So it's not just one data stream.
Yeah. So infants don't have the text, but they have other kind of input. So they have multimodal input. They have the context in which the speech was done, plus some parental feedback. Okay. So all of this makes it different. So basically, what the child is doing is completely different from what the machine is doing, which is my point, is that now if you want to do what Alan Turing said, try to build a baby that would learn, an infant algorithm, then it will have to be constructed in a completely different way as is done standardly. So instead of having an expert human provide all the labels, you basically have a naive human interacting with the infant, but the interaction has is much weaker in terms of information content. Here you have a lot of labels, basically 10,000 hours of labels, and here you have like a small number of bits, and also the bits of information are ambiguous when the parents say to the child, no. What does that mean? I should stop stop talking, change the way in which the child was talking, stop breathing. I mean, what's the meaning of no? Okay, so it's a lot of ambiguity there. Now, of course, the input of the algorithm for the infant version of the system is maybe actually bigger than this one in the sense that it's more multimodal. The child doesn't know at birth that the language is carried by speech. It could be carried by the visual modality. Okay, so the system has to basically find a way to extract from the big and ambiguous, messy amount of data the relevant data for training a language system. Okay. So, given this, the project then would be to reverse engineer the human infant and build a system that would learn language just like infants do. Okay, so I'm going to divide my presentation in 3 parts. I probably won't have time to get to the end, but it doesn't really matter. I think for me it's important to get to the first 2 because they are illustrative of the nature of the problem. So the first part is trying to build algorithms that would do the same thing as the infant do. Okay, so how do we know what infants do? Well, that's what I've been doing in the lab for the past 20 years, recording the infant's behavior, the brain responses of the infant, make the infant choose by looking at a screen with different objects appearing, etc., etc. And so if you cumulate all of this in a single graph, you have here a timeline of the infant in months, so during the first year of life. And then these boxes represent landmark achievements that the baby has accomplished during this first year of life across the different levels of language. So you have here the consonants and vowels, you have the intonation of the language, you have the words, and you have the semantics of the words. And so as you can see, learning occurs very quickly, very early. Actually, at this point, they don't talk. Infants just babble. But at the same time as they babble, they have already figured out some typical distributions of the consonants and vowels of the language, and also actually some words and even some meanings of words. Okay. So all this is going on in parallel and very efficiently with actually even less data than what I've showed for the 4-year-old. Okay. Yes?
How do you know experimentally that the children recognize the virus or
yes,
clauses or something?
Okay, so this basically are experiments like this. So you can do, there are several things you can do with either EEG or infrared spectroscopy. You can present stimuli to the baby and look at the response of the brain. So when you have learned a category, for instance, there are asymmetries that you have. If you know a category very well, you present the center of the category, and then you present something that's not in the center. That's sort of more difficult to discriminate than if you go on the other direction. So these are asymmetries that you can measure with this kind of techniques. You can.
Which part of the brain?
Well, you just measure whether the infants know the distinction between pa and ta, for instance, or between ta and ta. So these two sounds are used in some Indian languages. You find that actually newborns or very young children, French children, can do this distinction, and then they lose the distinction. So all of these effects can be measured and establish this kind of graph. I don't have time to give you a whole history of the psycholinguistics of babies, but for now you have to basically believe me that that has been established. Now, there are distinctions, of course. Basically, each of these boxes that have been made here have been replicated, but still we are not completely sure that it will be found in all the languages, etc., etc. So we have, unfortunately, the number of baby labs is not that large. So I'm going to concentrate on these two levels here, finding the phonemes and finding the words. And so the question I was asking myself, okay, so how could you build a system that would just do that? Find some words, okay, extract from the continuous speech words that are relevant for the language, and also start to focus on the contrasts that are useful in language. Like, for instance, know that in French there is no distinction between ta and ta, whereas in Hindi you have a distinction between ta and ta. How does the child know? So, yes.
Isn't it even controversial whether this typical decomposition into phonetics, syntax, and semantics from classical linguistics is really a useful distinction in language learning?
Well,
in computer, I think in computer language learning, it's sort of indispensable. They don't use that anymore.
Well, no, they use it. They completely use it. I mean, even deep learning systems, they still have different stages. Yeah. No, yeah, I mean, you find, I mean, in any field of research, you find people who say that the particular construct does not exist. And you can do that for any construct. So that's just a fact of the sociology of science. Well, what's not clear, I mean, so what is clear here is that if you take a Japanese child and you test the Japanese child at 12 months, that child will not distinguish between ra and la, which are two phonemes, distinct phonemes in English, whereas the English child would distinguish. So you have already learned something. Now, does it show that the child has the category, discrete category? We don't know, but we still know that they have learned something about the language which is relevant, and that's the kind of thing we want to model. It doesn't matter really if there is a level like phonetics per se. What matters is you have phonetic learning going on. So basically, what I've been trying to do in the past 3-4 years was to build algorithms that would reproduce the same kind of effect that we have measured in babies with machine learning. And so, because it's a difficult problem, and it was a bit too ambitious for my small team, what I did was to organize challenges for engineers. And I say, well, imagine I give you speech in a completely unknown language. You have no idea what the language is. I don't give you any labels, no transcription, no text, just the speech. Can you do two things? One is to discover things like consonants and vowels. Or if you don't discover consonants and vowels, can you find representations that have the same functional effect? Like, for instance, they would fail to distinguish ra and la if they are proposed in that language, in Japanese, for instance. That's the first track of the challenge. The second track was to find things like words, like chunks that may not really necessarily be words. They could be smaller, larger, but they would roughly correspond to words that are frequent in a language. Okay, so these were two challenges that were organized at engineering conferences, and actually a lot of people responded. They were interested in that problem. And so I can tell you a little bit about these two problems. So the first problem, as I said before, was to discover something equivalent to consonants and vowels, even though they may not be discrete. So actually, if you look at the history of speech processing, a lot of people have wanted to do that for a long time. So first of all, you have people basically inspired by neuroscience, auditory neuroscience, who have tried to devise acoustic features, so they wouldn't be discrete representations, but they would be representations that would be tuned for language, very good for language, for making distinctions that are relevant for language and ignoring distinctions that are not relevant for language. Like, for instance, distinctions of speaker, who is speaking. That's not relevant linguistically. So you want to devise features that would focus on this aspect. So you have a whole line of research devoted to devising what's called acoustic features, okay, that specialize for language or good for language. Then you have researchers who have been working with neural networks. So you have this rather old paper by Kohonen using self-organizing maps, trying to discover automatically vowels and consonants. And more recent papers have done deep autoencoders. And then you have models that are more inspired by linguistics and try to discover discrete units by doing some form of clustering or Bayesian, non-parametric Bayesian model. Okay, so these could look like completely different models. So how would you compare them? In the end, we want to compare them with what the child is doing. Okay, we don't necessarily. It's not a problem if you discover a representation that's not discrete. What we want is that it has the right property, and so the way in which we evaluated these models was to use a task from psychoacoustics, which is a discrimination task. So we want that the model, so imagine you have a model that discovers some representation, like a continuous representation. What we want is that this model is able to classify tokens of speech sounds according to whether they make a linguistic distinction or not. So we want that this token of ga, spoken by one speaker, is closer to a token of ga than a token of ba. Okay? In that case, we say, well, the system is able to represent the distinction between ba and ga. Even though it's not a discrete representation, if it can do this classification with zero error, we are happy. We say that's a good representation that captures the linguistic distinction and ignores the distinction about speaker. So this is a metric we developed for the challenge. And that just gives you an idea of what if you have an IBX error of 5%, it means that basically the two categories are rather well separated. And the nice thing with this evaluation is it can be applied to any representation, continuous or discrete. And so we could compare the models. So we got lots of responses to the track one over the 2 years of the challenge. I can't summarize everything, all the papers, of course. But I can give you an idea of what people have proposed for solving this problem of learning a representation that's tuned for a particular language with just raw speech. And it's basically a bunch of ideas that all boil down to one main idea. And the main idea is information compression. So if you take if you try to evaluate the number of bits you need to encode a spectrum, a whole spectrum of speech utterances, you have a certain number of bits per second. If you compute the same bit rate for a description in terms of discrete phonemes, then you have a 200-fold reduction in information. So really phonemes or discrete categories or whatever are tremendously compressing the acoustic information, only retaining the linguistic contrast and removing everything else. So basically all of this idea, computing low-dimensional embeddings or doing some probability codes or discrete codes, they all go in that direction of compressing the information as much as possible. So that's the main idea. Now, in the track one, we had other ideas that emerged. One of them is related to the first one of information compression. It's talker normalization. So the idea is that among the information that you have in the spectrum, yes?
So in the training data, you need different locator?
Yeah, so the training data, that's a very good question. In the training data, we provide lots of speech, like 10 or 50 hours of speech, or even now we give like 200 hours of speech. That has been collected with various speakers, and we provide the labels of the speaker. We say this is speaker A, speaker B, speaker C. We give that. We assume that babies are able to distinguish the speakers, not only by their sound, but also by their appearance. So we assume that babies are able to solve that task. Actually, it's not completely trivial either, but that's what we provide the people. So given that...
You think it's enough multimodal information?
Well, of course, it's extraordinarily impoverished. It would be like a child basically locked, not being able to move and just being able to hear what is spoken around, okay? So the question, of course, is not to imagine that you can solve everything with this challenge, but the question is how far can you get with that compared to the supervised system. Okay, so the other idea that people looked at is precisely this idea of speaker and try to remove the speaker information from the representation. So a number of techniques have been tried. Most of them are a little bit of hacks derived from the old speech technology. Some of them are called vocal tract length normalization. So it's basically trying to warp the spectrum so that the distribution of the frequencies is the same across different speakers. There are more subtle and complicated methods that have been used, but basically people have used what was done before in the area of HMMs in speech and apply that for normalizing, and actually it works quite well. Now the second idea, and this is an idea that we have been pushing in my team, was the idea that these two challenges, finding the phonemes and finding the words, are actually related. And they are related because language has some structure. Language is a hierarchical system, and the realization is that if you know what the words are, then that could help you to know what the phonemes are. And the reason is that if you know that two words are the same, you know that all the phonemes are the same. Okay, that's obvious. Now, if you know that two words are different, actually, on average, 90% of the phonemes are different. So obviously, you have in words in languages minimal pairs like pain and bain. Okay, that just differ by one phoneme. But on average, if you take random pairs of words, you get these statistics. So you can rely on that to give you a signal on the phonemes. And the idea is that it's maybe easier to find the words than to find the phonemes. So that was the idea. So the idea is that you go from the speech, you discover some words, then you use these words with this technique to refine your subword units, and then you could sort of do some iterative learning like that. Yes?
When we are talking to a child, usually to an adult talking, there are sentences which make sense. So there are some correlations.
That's right. Yes.
Strong correlation. Yeah. Now, if you do experiments, you could present unrelated, random chosen words. So, does it make a difference?
Yeah, so babies recognize the words. If you present them pairs of words that exist and words that do not exist in the language but are legal, they prefer the words that exist. So it means that they have, at 12 months, that's how we know that they have extracted some words, is that they recognize the shape of the words. Even if they may not know the meaning of them, they know that it's a shape in the language. So that's exactly the idea, is that they would be able to do that and that will help them. So what we did was to use a Siamese network architecture, which has been used previously in vision, where it's basically a neural network, feed-forward neural network that's being duplicated, cloned. So these two networks have the same weights, but they give different input. So you give them pairs of words. So imagine that you give rhinoceros to the left, rhinoceros to the right. Then you know that the phonemes have to be the same, even though they could be said by different people. So if you look at that little part, the N may look on the spectrum quite differently because the speakers have a strong effect on the acoustics. But because it's the same word, you know it's the same phoneme at this point. So what you do is you realign the two signals using dynamic time warping, and then you slide this little window to the network, and you teach the network to make the output representations closer if it's the same word, and more distance if it's different words. So that's something that we did in several papers.
But do you tell the network it's the same word?
Yes, so that's suppose that you have a lexicon, okay? Assuming that you have already a small or a certain lexicon of words that you have identified, you tell the network. So it's a supervised system, but it's self-supervised because the word have been discovered by a different system. Okay, I'm going to go to the word discovery later. So, so here we have, in this paper, we showed that this can scale to very large data set, but that's not relevant here. I'm going to actually skip some of the details, otherwise I will never get to the end. So what we did recently was to use the fact, I mean, the thing that we have, so maybe I can just summarize the main point of this idea here, is that the problem we have in language in general is that we have power laws everywhere, okay? So we have power law in the language distribution in the world, but also if you look at the frequency of the word in a given language, you have a power law, you have a few words that are extremely frequent. So if you do this trick of learning by pairing words, you end up being dominated by the few very, very frequent words in the language. And you don't use all the other words as you have learned. So what we did was to apply a correction on the frequency of the word, and that actually helps learning a lot. So this is like a detail at this point. I think I just want to summarize the track one results, is that people have, so how to interpret this chart here. So these are the two challenges, the first one and the second one. They were using different languages. So in the first challenge, we use English and Tsonga, which is an African language. In the second challenge, we use in German and Wolof. And the percentages mean how far you are from the performance of a supervised system. So supervised, it means that you have given the system all the labels, all the text, and you train it in the standard machine learning way. And if you are 100%, it means that you have reached the level of supervised system. If you are 0%, it means that you are at the level of the spectrum. You have learned nothing of that language. And you can see that basically these are different systems, some of them by the lab, some of them by other people. And some of them have very good performance, okay, very close actually to the supervised level. So it means that these ideas of using just compression or compression plus normalization, or the idea of using the lexical contrast can actually work quite well. I mean, it doesn't always reach, importantly for the African languages, it doesn't go to the 100%, which is interesting. These languages may be slightly more variable than the English, which is like more, it's a more stable language because it has like television and writing system and all that stuff. So that's, the language may be slightly more standardized, but this is doing quite well. Now there are other ideas that could be done, and many combination of ideas haven't been tried yet. So even though, I mean, the situation, I agree, is completely, it's a huge simplification compared to what the infant is doing, it's actually doing quite well. Now the second track was to discover words. So how would you discover words? One idea is to use the similarity, acoustic similarity, and looking for patterns. So in this graph here, what you have is the spectrum of a whole utterance, or whole corpus actually, and then you have another corpus there. And so a word in that representation, now in the matrix here is a matrix of distance for each frame instead of time on this axis and this axis. And so a word basically is a high similarity portion that goes in that diagonal part. Okay? So what the system is trying to do when discovering words is trying to find these patches of similarity and then cluster them. And when you cluster them, now you have a lexicon. And you can use now to say, well, that's how my sentence is cut into words. So, and now how you evaluate that, but you compare with the words that you have in the text in your language, and you can also evaluate the boundaries that you find. Okay. So people have tried various ideas on this, using either the idea that you can find syllables, for instance, very easily in the signal, and so syllable boundaries are natural boundaries for words that already give you a performance that's not zero. Then other people have done this basically improvement on this completely exhaustive search of patterns. And again, the performance here is what you get compared to a system that would have the best system that does word segmentation based on text. Okay, so that's our top line, and you can see that there the performance is not that great. It's actually not that easy to find words.
Is the prosody taken into account?
Yes. So some people have tried. We've tried to use prosody, and
it's not.
Well, it's disappointing. I mean, the whole lab is like a prosody champion, right? And but I was not very happy that actually prosody is not that helpful. In fact, I mean, the things that, well, I mean, prosody helps in the sense that there are cases where prosody is very clear, is when you have a silence, and that helps. But then if you want to go to prosodic differences within a sentence where there is no pause, then it's super difficult to actually use the prosody. And if you use it, it doesn't really help that much. So it's a bit disappointing, but and also what we found is that contrary to what we thought, we thought that the prosody would help, especially when parents talk to the child, and that's again not the case because when parents talk to the child, they make very small sentences anyway. And prosody doesn't really help there. So anyway, so there's a whole story about prosody that I could tell some other time. Yes?
So why is it so much more difficult to segment speech than segmenting written?
Well, yeah, so for the problem with speech is that basically you are solving two problems at the same time. So in a written case, you only have basically you have to find segmentation points. And you do that typically by trying to optimize the joint representation of the lexicon and the corpus, okay, the minimal description length, this kind of thing. But with text, you know when you have two identical words, it's just the identical representation. There you have to do clustering and segmentation at the same time, and it's actually much more difficult, especially because there is a lot of variability in some words, in particular function words. So if you take very short words like grammatical words, je, te, becomes je, things like this. So basically, frequent short words tend to be extremely variable acoustically, so they're extremely difficult to cluster. But because they are very frequent, they completely screw up the segmentation. So that's a problem that was not envisioned, and is actually an interesting problem to work on to try to make the system work better. That's a problem that infants are solving, because we know that they are extracting words, and they are also recognizing function words by the first year of life. So it's just that the models are not good enough.
We know that some speakers, from experience, that some speakers, particularly in a foreign language, are much easier to understand, to recognize than other speakers.
Right.
So do we know for which is the reason, which makes a distinction between the different speakers, and why some speakers are easier to understand than others?
Well, there are many ideas around that. That's one of them is the exaggeration in articulation. So some people will articulate with very exaggerated targets. So in the phonetic space, basically phonetic space is expanded. So that's what you find, for instance, when you read speech. When you read text, you take your time, you go slowly, and then you hyper-articulate, and then the speech is clear. It's actually easier for speech recognition to recognize read speech. When you go to spontaneous speech, then people start to don't reach their target, so they just will. In the end, it's all like basically all in the middle, like blah, 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 and it becomes extremely difficult also for the speech understanding system. What's important to keep in mind is that, in fact, some parents speak like that, but still babies learn the language. so it means that, again, the algorithm is much more robust than what we have currently. All right, so I'm going to skip about the current work we're doing on segmentation, because really there's no time. I just want to give you a little bit of idea of what we want to go next. So the next challenge that we are going to organize is to try to bring into the picture the idea that babies are not only listening, but they're also producing. So they are, even though they are babbling, it's not very, very good speech during the first year of life, they are producing some sounds which can be used as input for perception and the clustering and all that stuff. And then after the first year of life, they are talking. So now you have a system where you have this sub-word units. So this is the speech features. You have some sub-word units, and then you have the word units. These sub-word units can be used to repeat what they heard. Okay, and the fact that the system can basically do this kind of loop there could help constructing better representations. And so our next challenge is to basically ask people to build a synthesizer from, again, an unknown language without any text, okay? And that's what we are setting up. Now, we could continue. As you point out, there is also meaning going on. So one way to go one level up would be to incorporate topic modeling and language modeling. So you could imagine doing this. And we have done some preliminary experiments showing that even if you do very bad word segmentation, you can still use that to guess an idea of the topics of discussion. So topics are not that much dependent on function words. They are dependent on bigger words, and the bigger words are easier to find. So it's actually possible to derive some idea of the meaning, or at least the meaning similarities between words, because words that are similar meaning occur in similar contexts. So the idea is that the baby system there could start to try to assign some meaning representations to these units discovered automatically. And finally, but that would be like in maybe 10 years, you could start to now say, well, the baby is in a context, in a visual context, and in a multisensory context. And language is sort of connected to that, because in a particular context, parents talk about particular things. So there is a correlation between the context and the content of the speech. So maybe this grounding, these semantic embeddings to other modalities could actually help learning. So basically, you see that, I mean, the idea is to step by step build a system that would approximate more and more what the baby is doing, and at the same time, go also towards a system that people in technology would like, because now you have a system that can talk to you about things in the context. And that's typically what people want to build. They want to build something like the Siri system, asking the system to do something or to describe a picture, give me a picture of this and that, or play me a tune of this and that. And if you could do something like this in a language without text, then basically it means that what exists now in your phone could be spread in the 7,000 languages in the world and not be restricted to the only 1% of the languages. So basically, so that's what I've been trying to push, this convergence of interest between the people in machine learning and cognitive modeling. So very, very briefly, I think I have only 10 minutes or 5 minutes or 0 minutes. 15 minutes. I want to talk about the other project I'm doing, which is actually connected with this one, because you could see it as part of the top of the top system. We know that babies, at the same time as they are learning language, they're also learning about the world, okay? And they are building a representation of the world. And so with experiments which are sort of similar or related to the ones that have been run in language, we know that infants very early have some notion of objects and how the objects interact in the world. So I have done a chart which is sort of similar to the one for language, where now you have, during the first year of life, we have experiments showing that babies represent objects even if they don't see them. They have notions of solidity, that two objects cannot occupy the same space, and also start to group them into natural categories. And then they start to figure out slightly later on, but still during the first year of life, some notion of interaction between objects, like some objects are supported or they are going to fall, they can predict what's going to happen. They get some idea of gravity. So all of these abilities are emerging quite early, before infants have acquired the language. But of course, they are going to interact and be integrated with language learning at some point. And maybe these two modalities will help each other. So I've been interested in trying to also see what machine learning could bring to that problem. Could we build systems that would also acquire this kind of intuitive physics by observing or interacting with an environment? So it's actually more difficult to do, of course. But what I've done was, again, to set up a challenge, a benchmark for vision and robotic people. So I don't have the demonstration here going on, but typically the idea is that the system would be, an agent would be raised in an artificial environment, being able to interact with various kinds of objects, simple objects, geometric objects. And then we would test the system using basically the same kind of psychology experiment that we do with babies. So how do we know that babies know about languages, about objects? Is that we do experiments like this. I take an object, I hide it, and then I remove the thing that hides the object, and there's no object. And we measure the surprise of the baby. If the baby is surprised, it means that the baby had some expectation about the object should still be there, and it disappeared. That's surprising. If it's not surprised, then you can't really conclude anything. So that's typically how it's done. So you can construct a very well balanced data set where you start with two objects and you end up with two objects, or you start with one object and end up with one object, or vice versa. And this is like something going up and down like that. So these are the kind of tests that we are proposing to build, and we have already built a number of them and put them into a data set. So, okay, maybe, yes. Yeah, so I have a PhD student working with in Riyadh and the Willow in Riyadh team trying to solve that problem and building a system that would actually learn or discover or just perform according to infants, and it's actually very, very difficult to do. It's a tough PhD project. Okay, maybe in the 5 minutes that remain, I can try to tell you that all of this can finally relate back to cognitive science, which was my starting point. You could say, well, I think what I've showed you is that the problem is extremely difficult. Most machine learning systems don't behave like infants, so if you try to make them behave like infants, it's tough, it's difficult. And so maybe it will be useful for cognitive science in 1,000 years, but not before. But I think that's not the case. I think we can still use some of these incomplete models to tell us something about language acquisition and language development. And so one way in which we can do that is to go back and look at theories that have been proposed in the infant literature and test them with some of the models and see whether they hold or not. So one of the very old ideas, it's still an idea that's held by many people. It's like I called a zombie idea. The zombie idea is that parents are helping their child by talking to them in a special way. So parents will talk like this, extremely exaggerated. So it was the clear speech idea, is that the parents are expanding the vowel space like this. So they're making the targets, the E, R, U more extreme when they talk to their child. So this is an old study by Patricia Kuhl in 3 languages. And so the idea is that because parents are expanding this, they are helping the learning system to build the categories. So we have been trying to test that with a number of models or ways of measuring the signal derived from our models. And what we realized is that well, it's not necessarily the case that if we expand the vowels, it makes things easier, especially if what happens is that also parents are changing the standard deviation of the categories. So what happens when you measure the signal is that they're not only making R, E, and U more extreme, but they're also increasing enormously the variability. So you end up with categories that are more overlapping than otherwise. So this is here a measure. We did the separation of the categories. So there's a tiny increase, which actually in that data set was not significant. But the variability is increasing enormously. So now if you measure the discrimination, it goes down. So the parents are, unfortunately, not really helping the baby, at least in terms of this category overlap. So this is another representation. So here we look at a lot of different contrasts between consonants and vowels. And if the adult-directed speech is this axis, the infant-directed speech is that. So if the infant-directed speech is easier to discriminate than adult-directed speech, everything should be above that diagonal. And you can see that, if anything, it's slightly under the diagonal. Yes?
What happens if you apply some sort of curriculum learning where you start by speaking in a very exaggerated way and then gradually switch to more natural language?
Yeah, so we tried that. Actually, I don't have that slide because that's what we did. That's what we're doing right now. And we have just a paper that we just sent yesterday on that. So I didn't include it here. We tried that and actually it doesn't work. So if you start with infant-directed speech and you switch to adult-directed speech, you are worse than if you started with adult-directed speech in the first place. Even if you are doing we tried 6 different algorithms ranging from unsupervised to supervised. So really, it seems to be doesn't help. But on the other hand, if you use red speech, then it helps. But so it's possible to find stimuli that help the baby to learn. It's just not infant-directed speech. So parents may think that I don't know whether parents think that they're helping. They are doing something special with their speech, and that's found in many cultures. But it may not have the functional role of helping the infant to learn in the sense of helping the learning algorithms. maybe what parents are doing, that's what I think now, is that parents are engaging in a social relationship, and infants love the infant-directed speech register. They prefer to listen to this kind of speech. So their attention is attracted, they are more focused, and maybe they are helping in that way, because then otherwise infants would not know what to listen to. So that's a different way in which you can help the infant, not necessarily by making the category clearer, but focusing the attention so that he pay attention. So there may be some trade-offs going on there. So we basically, in the end, we run our automatic discovery system, et cetera, on these things, and that's the conclusion we have, is that basically infant-directed speech does not help. If anything, it's slightly worse for a variety of algorithms. So that's one line of research. Another line of research would be to derive new predictions. Now, if you have a system that discovers words automatically, we know, and you saw that it's difficult to find words, and the system will make mistakes. Now, we think that it's not good for the models because they are making mistakes. But maybe they are making mistakes because it's hard. And if it's hard, maybe infants are doing mistakes as well, and maybe infants are doing the same mistakes. So now you can turn the problem of the learning algorithms into basically predictions. So maybe if you don't know anything and you want to discover words, you will find things like dans la, c'est pour, quoi ça, va faire, which are like very frequent disyllables, which are basically compounds of two words or parts of one word, like quoi ça, it means that c'est quoi ça, n'a plus, y en a plus. So things like this that are chopped off by the algorithms because they are actually present in the signal. They don't really correspond to words, but it's just present in the corpus. So what we did was to take these predictions and present them to babies using the preferential looking paradigm that I was describing before. Actually, I didn't describe, but I was alluding to. So it works like this. The baby, when the baby is looking at in one, there's some light flashing. If the baby turns the head, you start to play some words. As long as the baby is looking, you continue. And if the baby is bored, don't look, you stop. And this way you can basically measure the attention dragging property of these words or non-words. And when you do that, you can, so what we did was to play this list of non-words, the frequent one and the unfrequent one, and we found that the babies are preferring the frequent ones to the non-frequent ones, which means that they have somehow extracted something like this. They don't do that when the frequency band is reduced, and they don't discriminate if you compare non-words like this with real words of the same frequency. So probably so basically that's interesting because now you can use these algorithms to generate new experiments. So in this study there, a more recent one, what we did was to compare different algorithms. Now you can take different segmentation algorithms. So this actually was done on text. So we hadn't run yet the one on speech. That's what we're going to do next. This was more proof of principle that you take a bunch of algorithms. So you take text, you remove the spaces, and the algorithm has to find back the segmentation. Okay. Now you take the segmentation, and now that gives you candidate words that the system has found. And what we try to do in this graph is to compare the predictions of these algorithms with the actual words that the infants know. Okay, so you can find norms of the infant lexicon at various ages that have been collected in many languages in the world. And you can see the correlation coefficient between the frequency as estimated by this algorithm and the vocabulary of the child. So that's the correlation coefficient. Okay, so you can see basically what's interesting to note is that each of these different algorithms have different prediction values. So some of them, like TP, that's a particularly stupid segmentation algorithm, correlates quite well with what the infant is doing. Whereas this algorithm is actually correlate better than the frequency of the text itself. Okay. So some more sophisticated algorithm, like this one, they actually have a better performance if you compare them with the adult lexicon, but they correlate less well with the infant lexicon. So this graph is complicated, so but I think the main point there is that you can compare now the prediction of the different algorithms and compare that to the infant and then go back to your drawing board. And I think for me the main lesson is that it's not necessarily the case that the optimal algorithm as defined by the adult standard is the one that predicts the infant acquisition. So it could be that infants are in the first year of life using some more simplified version of the learning algorithm, and that's what they are using. So you can see that I think doing this kind of computational modeling, reverse engineering is useful because it can generate new ideas about the infant. So to wrap up, if you want to do this reverse engineering, what you have to do is to collect data, realistic data, and that's what I showed with this big study on collecting the child-directed input in many different cultures, doing recordings, and that provides lower bound on the amount of data and quality of data you need to learn a language. And from this, we learned that human learning is much more data efficient than current machine learning algorithms. Well, I showed you then algorithms that has to be unsupervised or weakly supervised. And basically, I show you it's a difficult problem. Some problems are easier than others, and we're making progress. But in any case, it's not going to be a simple neural network. It's going to be a complicated algorithm combining different ideas, because language is a complicated system. It's learned as a whole. So basically, you have like a complicated system learning all the parts of language at the same time, but it has to be a very specific architecture. And then finally, you can come back to the baby and try to predict the development in infants. And there I showed that this approach can be useful even if it's not finished. So to finish with that's another quote of Turing. It's actually in the same paragraph, which is interesting because he says that presumably the child brain is something like a notebook, rather little mechanisms and lots of blank sheets. Our hope is that there is so little mechanism that it can be easily programmed. I think that's actually not true. So I think even though the original idea of Turing was a good idea, try to model infants to build an AI, adult AI, the road is still very long. So that's my team, and thank you very much.
Thank you. So mine's kind of a meta question. So about science. So you say that you organize challenges, and I'm not familiar with that idea. So what's the motivation for other people to take on these challenges?
What's the
motivation for other people to take on these challenges?
Why do they do that? I don't know. I think I was surprised there were so many people in machine learning interested in that. I think there are a range of, so if you look at the list of people who participated, there were a very small number of cognitive science labs that are interested, like I am, in the development of child. But then there were a very large number of labs interested in low resource language, ASR, because they know that the standard paradigm is not going to work. So if you want to build a system, speech recognition for Wolof, it's very difficult. There is not a lot of resources in Wolof, and there are actually languages in Africa which don't have any orthography. They are spoken by tens of millions of people, so you can do nothing with that in the standard approach. So they are interested in this unsupervised approach because it could be the next generation of AI or language technology.
Yeah, but there's no money prize. You just pose a question, and some other people interested in that question take it on and keep going.
No money, nothing. Engineers like to solve problems.
Yeah, I think they have their own too. Maybe reputation to call the attention to a particular problem.
Yeah, I think this cast of problem is starting to get more traction now. As people are, basically the low-hanging fruits have been collected, and now it's tough. We go into the long tail, and it's going tough, and people are realizing that they need to completely change their approach.
Yeah, you had made a point about things reducing to the idea of information compression.
Yeah.
So, first of all, I'm not sure if you were just referring to the phonetic level or in general, but the question I wanted to ask is, I guess language, many people point out it's very redundant in a lot of ways. So you're not always compressing information maximally when using language, and I wonder if you could sort of say what the relationship is of the, I mean, do you think that this redundance is, apparent redundance is actually hiding other kinds of information, or what's the relationship of this importance of compression to the apparent redundance of language?
Well, I think it's a good thing that language is redundant, because then you can learn it through that kind of procedure. So if you take just the example I gave between the words and the phonetic level, the way in which we use the phonemes is not efficient at all. So if you were to use phonemes like bits and build an ASCII code with that, basically you would combine all possible consonants and vowels and all the words will be very short, and we will use all the possible combinations. That's not what any language does. The language will use very long words, which means that the whole space is completely sparse.
I wanted to ask also, how do you define information? It's a purely statistical.
Oh yeah, just there I measure the number of bits in a very stupid way. I mean, obviously measuring number of bits depend on the model you are using to encode your language. So I was just using a simple representation, like just the number of bits you would take to encode a letter or phonemes, and I measured that by second compared to what you can get. So. But I guess I think you're right. The redundancy of language, I think, is a very important property. It may, I don't know whether it's unique to that modality, whether you have that also in the domain of vision. I don't know, but you have certainly this hierarchical structure, and at each level we don't exploit the whole combinatorics of the level below. So it's each level, hierarchical level, is sparse in terms of the units below, and so I think that's an essential property of language, which makes it learnable. If we were more compact and more efficient in coding language, probably it would be extremely difficult to learn. Yes, okay, thank you.